Anyway, what we will be talking about today is knowing today what will never happen tomorrow. Basically, this is a quick and dirty presentation on how we can start using online monitoring as a first step to asset management. So, nowadays, it's a little difficult. It's a little dangerous to send people out into the field just because of what's happening around us. So, if we can remotely monitor our assets, that will be great. So that's what we're going to be talking about today. So here's the scenario. The demands that you have on your electrical system, it's very high. Now, your businesses require round-the-clock operation, allowing for a very, very limited time for preventive maintenance. Well, I remember preventive maintenance, particularly for transformers, used to be like 3 days, 4 days. Now, sometimes we're given 8 hours, sometimes even 4, just because people don't want to shut down because they when they shut down, even for preventive maintenance, sometimes they actually lose money for it or they lose market share. Now, in that case, maybe it's a good idea to have a round-the-clock monitoring system to actually ensure the safety, reliability, and efficiency of the system. Just because continuous operation can result in premature aging of electrical components and of course, failure to acquire predictive and preventive maintenance data can result in catastrophic process and economical impacts. Now, we can talk about safety, preventive maintenance all day, but at the end of the day, it's all about economics. How much does it cost for a blown transformer? How much does it cost you for an unwanted shutdown? Apart from the raw materials that you will be losing, production downtime, and if you're a company that's producing fast-moving consumer products, how much is it going to cost you if you lose market share? So it becomes a very, very monetary thing, no? So we will be talking about more on insulation. So what are the effects of deteriorated insulation? One is line-to-line faults, short circuits. One is line-to-ground faults and short circuits to exposed conductive parts, the ones that are capacitive in nature. Give me 1 second right here. Now, here's just a little bit of a tidbit that I got off the internet. The source is right here if you guys want to check them out. Fires and industrial manufacturing properties. I'd like to point out a few key things in terms of the statistics. 24% of lighting and distribution equipment, electrical, makes up 24% of the fires, at least according to the NFPA. However, that electrical distribution and lighting equipment, transformers and power supplies only accounted for 7% of the fires, but 46% of direct property damage. So it becomes a very, very essential part of safety, fire hazard, and all that other stuff. So insulation becomes a very, very important part of the work we do on a daily basis. So what are the contributors to electrical faults? Number one, whenever you have over voltage, over current, harmonics, lightning, magnetic and inductive influence. In short, if you had bad power quality, electrical safety is also compromised. So we never really separate electrical safety and power quality because you can't have one without the other. Others are mechanical influences. Whenever you have shock, impact, installation flow, penetration of foreign bodies, if you have dirty panels for that matter, it becomes a very dangerous situation. Environmental effects, higher temperatures, moisture, chemical influences. There are some facilities out there that have a very corrosive atmosphere, and that chemical influence becomes quite an important part whenever we're monitoring for electrical safety. Of course, whenever you have pollution and pests. I really don't know why ang mga daga paborito ang XLPE, but yeah, they love nibbling on that cable. You have natural equipment aging, of course. Sometimes when they're older, they're accelerated by excessive heat and moisture. And just like these guys right here, unsafe practice. So I guess everyone will be agreeing with me that insulation resistance is kind of like the decisive factor for a safe, reliable, economical, and continuous operation of any electrical system. Now, whenever we have insulation faults, whether it be on a grounded system or an ungrounded system, the first challenge is to actually detect it. Even worse, if your boss or whoever asks you to locate it, it becomes very, very difficult. To be honest, the easiest thing to do is to actually eliminate it because something already happened. Madali nang hanapin kasi may nangyari na. Again, the question we want to ask everyone else is, kailangan ba umabot pa tayo doon na may mangyari bago natin aksyonan? No? And that becomes rather a bad practice for asset management. Now, we will be talking about two things. One is the ungrounded system and the other one is the grounded system. Now, over here, the IT, that's not information technology, it's actually called isolated Terra. Isolated is how it's connected, and Terra is the ground. So you have on the grounded system, Terra Terra, Terra neutral, coupled Terra neutral, so on and so forth. No? So just to quickly discuss the difference between the two, basically, on an IT system, there's no direct connection to any live or current carrying parts. However, on a grounded system, the neutral conductor and the protective earth is connected at star point, and this is what we usually see here in the Philippines. No, ito yung tinatawag nating bonded, so to speak. Now, that's the main difference. There's no direct connection between live or current carrying parts. So even if you had a Y secondary, you can still have an ungrounded system. Only this time you're going to be on a standard 5-wire system. Now, it begs the question, which system is going to be safer? The most common answer that I get is usually, it has to be the grounded system. And the answer is application dependent. Depends on where you're going to be using it. Let's say for a grounded system, you had expensive equipment with rather, very low people interface. And if you wanted to save that equipment, of course, during the event of a first fault, you want that thing to shut down. Yes. However, in a hospital, in an event of a first fault, do you want the system to shut down? So that doesn't work that way. It cannot shut down in hospitals. We know that for a fact. That's why even in hospitals, it's in the standards. In the US, it's NFPA 99. In Europe and the rest of the world, it's under IEC 60364-7-710, and locally in the Philippines, under the PEC's Article 5.17. No? And those standards are actually pointing to an ungrounded system in operating theaters and critical areas, monitored by some form of insulation monitor or line isolation monitor, and it will be using an isolation transformer as well. Okay. Just to add, the fault current in an IT system is low in an event of first fault. The protection device will not trip in the event of first fault. Not unless the fault is symmetrical, then that's the time it would usually come to a fault. Now, what happens if we do experience leakage current in our body? This is according to the IEEE. At 0.5 milliamps, this is what we call the threshold of perception. Yeah, that's almost instantaneous exposure to about 10 milliseconds. At about 5 milliamps, this is what we call the let go threshold. At about half a second, at about 20 milliamps, respiratory paralysis, fatigue, and pain. And depending on your body impedance, anywhere between about 70 milliamps to about half an amp, ventricular fibrillation. So yeah, it becomes very, very dangerous now. Now, this one above 2 amps wasn't exactly in the IEEE. I just read this somewhere, but it looked very, very interesting. But you would have sustained myocardial contraction, burns, internal organ damage, loss of muscle ability. So it's probably going to hurt. That's the thing. It's probably going to hurt. So how do we monitor insulation integrity in the first place? Again, with two systems, you have the grounded and the ungrounded system. For the ungrounded system, we will be using insulation monitoring devices such as these things, and probably an insulation fault locator, which is this one, or a portable insulation fault locator, which is this one. On a grounded system, it's slightly different. We will be using residual current monitoring systems and residual current fault location systems. And the measuring principles I will be discussing briefly as we go along. So before we go into the measuring principle, what's the idea behind monitoring in the first place? Let's say you have this. This would be insulation monitoring for ungrounded systems. Right out of the box, according to the IEC, insulation monitors should give you a first alarm after it reaches 40 kilo ohms. And the critical fault will be at 10 kilo ohms. So that's the first alarm, and this is the second alarm, which is the critical fault. Now, the difference between your critical value and the first alarm is basically your advantage in time, wherein you can actually schedule maintenance. Now, for the grounded system, it's slightly different. Here, the set point for residual current will be dependent on your protection goals. Are you protecting humans? Are you protecting equipment? Are you protecting from fire? Or is it plant-wide protection? So dependent on your protection goals, depending on the calculations you've done, that's where we set our